Lecture 5B, heat and work, and we will be doing some related problem. Example 4.1 might be a different number in your book. Consider as a system the gas in a cylinder as shown in figure 4.7 over here. The cylinder is fitted with a piston on which a number of small weights are placed. The initial pressure is 200 kPa and initial volume of a gas is 0.4 cubic meter. Let a Bunsen burner be placed under the cylinder and let the volume of a gas increases to 0.1 cubic meter while the pressure remain constant. Calculate the work done by the system during the process. So if you can just look at our initial formula for the work done, this was the formula. Work done is equal to PdV changing from state 1 to state 2, and make sure the system is having gas in a cylinder. That means like we will be using some ideal gas equation rather than the stream table. So work done in a constant pressure process, if you take the pressure out from here, so that would be a constant pressure process P and dV, so something like this, and you would be end up with the formula which would be equal to P V2 minus V1. Make sure the volume over here is actually the total volume, as the unit of the volume is cubic meter, not cubic meter per kg. Work done would be equal to pressure multiplied by the change in volume, that would be equal to 12.0 kilojoule. So that's what actually it was a simple question anyway. Now consider the same piston, the same piston and same initial condition, but at the same time the Bunsen burner is under the cylinder and the piston is rising. Remove the weights from the piston at such rate that during the process the temperature of the gas remain constant. So that means like we are talking about the isothermal process. And let me show you like why we are using the Bunsen burner, or why the Bunsen burner is used normally. Bunsen burner, if you can imagine, there is a knob under the Bunsen burner, and Bunsen burner is used for the variable heat actually. So you can change the heat in a Bunsen burner. While if you are looking for the spirit lamp is normally used for the constant heat process, while Bunsen burner can be used for the variable heat. So the process is isothermal process, as the temperature is seen over here. So for the ideal gas equation, PV is equal to MRT. Remember that one in the last lecture. And we did derive some equation like this somewhere. PV is a log of V2 by V1. Or if you remember in the last lecture, we did say like RT log of V2 by V1, and the RT is equal to PV is equal to RT, if you remember from the top bit. So PV is equal to R to P1. V1 would be log of V2 by V1. So P pressure, initial pressure is there, initial volume is there, volume V2 is there, volume V1 is there. Put the value and you will get the answer, which is actually 7.33. So that's what actually it is something like in a isothermal process, the pressure, the work done would be 7.33. Let me mark it down over here. So 12.0 kilojoule in a constant pressure process and 7.33 in a constant temperature process. Now, part C, consider the same system, but during the heat transfer, remove the weight at such a rate that the expression PV raised to power 1.3 is constant. In a last lecture, on a last bit, I just say like PV raised to power, when we have got PV raised to power n is equal to constant, that means like the process is polytropic process. So it's a example of a polytropic process, and that what actually say like rate that the expression PV raised to power 1.3 is equal to constant describe the relation between the pressure and volume during the process. Again, the final volume is same 0.1 cubic meter. Calculate the work done. In a polytropic process, in the last lecture, if you can go, that would be P2, V2 minus P1, V1, 1 minus N is actually equal to the work done in a polytropic process. Uh, V2 is given, P1 is given, V1 is given, N is there, that means like PV raised to power N is constant, so that means N is equal to 1.3, N is there, The only thing actually we do not have it actually P2. Now looking back to it, PV raised to power n is constant. That means like P1 V1 raised to power 1.3 is equal to P2 V2 raised to power 1.3. So that means like that PV raised to power n is constant. Just rearrange for the P2 somewhere, and you will find like P2 would be equal to P1 V1 minus V1 divided by V2 raised to power n. Make sure the power raised to power n is just on the volume rather than on the whole PV. So if you solve it, that would be equal to work done would be equal to 6.41 kilojoule. Now the same thing, same initial condition, but now the uh, but let the piston be held by a pin, so the volume remain constant. So now the process is constant volume process. In addition, let the heat transfer end until the pressure drop to 100 kPa, whatever it is actually, whatever even the pressure drop or whatever it is. If you are saying like volume is constant, so there would be no work done. So work done would be equal to zero for a constant volume process. Now showing on a PV diagram, and let's check it different values. So we have got a highest work done in a constant pressure process. Then we have got in a isothermal process. Then we have got in a polytropic process, and the lowest work done that could be possible would be the in a constant volume process, isochoric process. So in the same thing, if you look at the lecture number 5a, we did select the work done is actually represented by the area under the curve. So if we keep the pressure constant and change the volume, so our graph will look something like this. So going from 1 to 8. If we then for isothermal process, PV raised to power n, sorry for that, PV raised to power n, that means like it will be something curvy over here. Then we have got PV raised to power n is constant, so that would be something like this. And lastly, when the volume remain constant over here something, so that means like it would be something like this. So if you can look at it, the maximum area that is possible would be under the constant volume process. Then we have got the isothermal process, and obviously later on then we have got for the polytropic process, and obviously there is no area under the curve in a constant volume process. Now let's go to the another example 4.4. A piston and cylinder setup shown in figure 4.12 somewhere down there contain 0.1 kg of water at 100 kPa and 500 degrees centigrade. Water is now, so we have got a problem which relates to the water itself now. The water is now cooled with a constant force on a piston until it reaches half of its initial volume. After this, it is cooled to 25 degrees centigrade and while the piston is against the stop. Find the final water pressure and the work in the overall process. Show the process in a PV diagram. So this is a problem of water, and we would be using the steam table. So initially what it say like initially we have got a piston and cylinder arrangement, state 1, let's say, and we are actually cooling this piston and cooling the piston so it reach half of its initial volume. So we have got 1A, which is half of the initial volume. The stop is at the half of the cylinder. Then when piston reach over here, somewhere here, the cooling would still continue to 25 degrees centigrade while keeping the volume constant, and that would be our state 2 somewhere. We can just write it state 1, 1, 2, 3 or whatever, but as the book is saying 1, 1A and 2, we will stick to 1, 1A and 2. Find the final water pressure. So water pressure at state when we are at 25 degrees centigrade, and show the work done in overall process. So first thing first, Let's go to initial condition, which is 100,000 kPa and 500 degrees centigrade, and find the volume at state 1 actually. So 1000 kPa would be equal to 1 megapascal, and at 1 megapascal 500 degrees centigrade, let's check it, which what is the condition now. So moving to one saturated temperature, saturated steam table. So 1 megapascal, sorry, so 1 megapascal is somewhere here, and corresponding to 1 megapascal, if you can check it, the temperature is 179.89. So that means like, as our given temperature 500 degrees centigrade is there, at 1 megapascal 500 degrees centigrade, we would be in a superheated condition. So let's move to superheated steam table. Superheated steam table and find 1 megapascal in superheated steam table. So if I can look at this one, so I have got the 1 megapascal somewhere here. 1 megapascal, 500 degrees centigrade, and we are interested in the volume at 1 megapascal 500 degrees centigrade. So at 1 megapascal and 500 degrees centigrade, I have got a volume of 3541. So moving back to the question itself, it's like at 1 megapascal 500 degrees centigrade, we have got the initial volume which is 53541. It might be having different steam table, and that is cubic meter per kg. Now, when we are when we are cooling from V1, it's like when we reach the stop, which is somewhere here, the volume is half of what I'm saying, like volume would be divided by 2. So V2 would be equal to V1 divided by 2, which is equal to 0.17706 cubic meter. Now, 0.17706 cubic meter, we will be checking in a steam table again, and obviously we will be looking at the pressure, which is actually the same pressure. It's say like the piston is cooled at a constant force, so P1 would be equal to P1A. So the pressure which was initial is actually the now the same pressure as well. So at 1 megapascal, again we would be looking at the volume. So 0.17706, if I could check it. So let's go to same saturated table, warm saturated. So let's check the condition of the steam somewhere. 0.10 at 1 megapascal, the condition is 0.177 something. So if you can imagine, 0.177 is less than Vg and greater than Vf somewhere. So that means like we are inside the vapor dome. So 0.177 the 17706 is inside the vapor dome. So now if I would just write on a PV diagram, so initially what I'm saying, like at 1 megapascal and 500 degrees centigrade, I was somewhere in a superheated condition. Then it was cooling, and in a cooling the volume would reduce while keeping the pressure constant at its state something. So keeping the pressure constant and changing the volume to initial to the half of its initial condition. So we have got a volume which is 0.17706. So now 17706 lies inside the vapor dome. So that means like we are in a two-stage region or in a mixed stage. So as we know that we have got volume now, which is actually in a mixed region. So keeping the same volume constant and decreasing the temperature to 25 degrees centigrade. If you go down on a PV diagram, so you can imagine like even if we are on a state 1, which is 1A, and we go down to state 2, which is actually at again in a mixed region, so we would be looking at the saturated temperature, sorry, saturated steam table at 25 degrees centigrade, and at 25 degrees centigrade again we will be in a saturated region. So that what I mean to say, like, as my volume V2, sorry for that, as my volume V2, or if I'm like say 1A is in a saturated region, keeping the volume constant and decreasing the pressure, we would be still in a saturated region. So that means, like, at state 2, 25 degrees centigrade, I am still in a saturated region. That means like in a mixed region. So going back to the temperature table and temperature table at 25 degrees centigrade. So temperature at 25 degrees centigrade, I have got a pressure of 0.003170, which is equal to 3.170 kilopascal, if I would say. So that means like our P2, which was required, so the pressure at state 2 is equal to saturation pressure, which is equal to 3.169 kilopascal. Now, it's like find the work done between the process 1 to final process 2. So if I'm looking at process 1 to 1A, this is a constant pressure process. Let me rub it down for again, if I say. So if I'm going from process 1 to 2, 1A, this is a constant pressure process, or 1A to 2, it's a constant volume process. So the work done will be only and only possible in this region. That means like it is a constant pressure process, while there will be no work done in a constant volume process. So the only work done would be from state 1 to 1A. So going from that, again, formula PdV, and I've got mass right now. So MPdV. So pressure P1 is given, volume V1A, which was actually the final volume or the half of the volume, minus the initial volume, and obviously plus 0. 0 is for this one, 1 to 1, no, 1 to 2 actually. So the final work done from 1 to 2 would be equal to minus 177.7 kilojoule. Why we have got minus now? As we are decreasing volume, the work done is on system by the surrounding. So that means like it will be a negative work done. Make sure the negative sign does not mean like the work itself is negative. Negative sign mean like the direction of the work done is on a system by a surrounding. So there is no like negative or positive. That mean like only it show the direction of the work done. I hope you understand that one. If you have got question, please post it on the classroom, and I will be able to answer this one. Thank you very much. Have a nice time.